Great. So today we have Kristin DeVleming with us from UC San Diego, who's going to be speaking to us about wall crossing for K-moduli spaces. Take it away, Kristin.
Great, thanks, Vance. Welcome. I'm happy to be here virtually, a little different than in person, but I hope I can tell you a little bit about K-stability and what K-moduli spaces are. I am also happy to leave out some of the technical details and give you an overview, but I'm happy to answer questions as they come up. I have the chat open. I don't know what the policy here is. If you answer questions in chat or in person or anything, I'm happy to answer. So just feel free to stop me, and I will do my best to get us all on the same page. So I'm going to talk about a project with a general flavor of moduli of varieties, but focus specifically on the case of curves. And everything that I'm going to talk about today is joint work with Kenny Asher and Yu-Chen Liu. They're both currently at Princeton. Kenny's moving to Irvine in a few months. So let's get started. I guess we will start with a setup with the motivating example of today's talk. So our plan will be to find ultimately proper or compact moduli spaces, parameterizing isomorphism classes of plane curves. And there's a reason we'll be talking specifically about plane curves, but we can generalize this beyond this as well. So plane curves of degree, how about we say at least 4? So a plane curve to me is going to be a curve inside P2, and we'll work over the complex numbers. And C is defined by a homogeneous polynomial of degree D. So if you want a moduli space, this should be a space whose points correspond to these isomorphism classes of curves. And you can sort of get your hands dirty and just construct it if you leave out the word proper. So I could consider the space of all plane curves of degree D, take the projectivization of OD, and I could consider the locus of smooth plane curves inside this projective space. So each point of U corresponds to a specific isomorphism class, or at this point, just a specific smooth plane curve. And so this is just an open subset of a projective space. So you can count the dimension. And since I say isomorphism class in the plan of the problem, then we want to quotient this locus. So this locus just parameterizes the curves, but we could, sorry, my dog's barking at something in the background. That's a little fun, fun extra zoom noise. But we can take the locus of smooth plane curves and quotient out by the automorphism group of P2. So because the degree is at least 4, every isomorphism of these plane curves is in fact coming from an automorphism of projective space. And this is then a parameter space. We've quotiented out by isomorphism, so it becomes our moduli space of smooth plane curves. Up to isomorphism. The main thing about this space, depending on your motivation and point of view, and maybe why you care, is that this is not proper. So, if you're an enumerative geometer, maybe you care about proper moduli spaces to do intersection theory or study some sort of actual counting problem. How many curves in the plane of degree 5 have 2 cusps, things like this. But maybe you want a proper moduli space to study the limits of these smooth plane curves, right? If you think of proper meaning compact, this space is not proper, so it is not including all of the limits of families of plane curves. So if I have a family of curves, what can it degenerate to? And that's really my perspective, but there may be many reasons you would want to consider this. So that's the question that we'll try to tackle.
Sorry, when you say, this is a really naive question. When you say it's not proper, you mean it's not proper over something? Over what in this case?
In this case, we're just talking about over C. Everything's over C. Yeah, so it's not a proper, I mean, this space actually is, we're just looking at smooth curves here. So this is actually just a variety, but it's not it's not a proper variety over C.
Thanks.
So our hope maybe is to compactify this. And in order to compactify this, we need to include singular curves. So, I mean, you could have asked this question from the beginning. I didn't maybe make it precise, but for some reason I took the space of all curves and just restricted to the locus of smooth curves, which made it not proper because smooth curves can degenerate to singular ones. But maybe I should just include singular curves at the beginning and see what happens. But I mean, really, this is a general question. What singular curve should we include? What is the minimal number of singular curves? What singular curves do I need to include so that the actual moduli space has good properties? What singular curves do I need to include if I want the curves to only have mild singularities? So really, I mean, we could ask ourselves, which curves do we want to include to compactify? And in general, when you're talking about moduli spaces of varieties or moduli spaces of curves in particular, there are many different answers of what you can include. So since we're talking about plane curves, we'll stick to a couple of perspectives. So, one option to make a compact moduli space, you could use geometric invariant theory. So GIT, geometric invariant theory. And without going into too much detail, roughly the idea behind this is that I can make a moduli space. I'll call it P bar GIT, or moduli stack perhaps, which is not just the set U of smooth plane curves inside my projective space, but it'll be a set called U semi-stable, with quotient out by the automorphisms of P3. Here, U semi-stable is some set that includes U inside of this projective space. And U semi-stable, USS, this is the locus of what are known as GIT semi-stable curves. And the idea here is to consider the action of SL3 or the automorphisms of P3 that we have on the set U and define a notion of stability with respect to that action. So I think maybe what's the most useful is to give you an idea of what the curves here are. What curves have we added? So I guess it's first of all a theorem of Mumford that this is indeed proper. So it is a compactification of our moduli space, but it parameterizes quite singular curves. So for instance, they could be everywhere singular. They could be non-reduced. And maybe we'll just draw a picture of what specific curves are included in the first case of interest. So let's start with degree 4, the smallest degree. And the moduli space here of GIT stable curves or GIT semi-stable curves, just draw a picture. This will be my picture of P4 GIT. And we have some special loci. So we have a special point, draw it in pink, which I'll call Q4, maybe. And this is the class of a double conic. So take your favorite smooth conic in P2 and square that equation to get a quartic curve. So this is a GIT semi-stable curve. It's in fact, this point represents a class of curves, but this is the unique polystable member, and it's everywhere non-reduced, so it's everywhere singular. So it's pretty singular as a curve, and then there's some other special loci. So I'll draw in blue. There's a locus that parameterizes curves with tack nodes, which are some special singularities. of the form x squared plus y to the fourth equal the vanishing of that equation. So it's, like 2 tangent conics. And away from the colored loci, all of the curves have at worst cusps. So I won't draw too much on the picture because it's just going to get very, very cluttered, but away from these loci, all of the curves parameterized by this moduli space, P4 GIT, have at worst cusps as singularities. So that means the curves that are parameterized are either smooth, they have a node, or they have a cusp.
And can an individual curve have multiple nodes or multiple cusps?
Yes, yes. So, I mean, even in this picture, in the case of the TAC nodes, the polystable representatives in this curve all have 2 TAC nodes, exactly 2. And same for cusps. There's a bound on the number of cusps and things that one can have, which I don't remember off the top of my head, but yes, multiple nodes, okay. Multiple cusps, okay.
Can I ask, what does the complement of view inside the GIT quotient look like? I mean, is it a divisor, normal crossings divisor? Probably not. I mean,
So it is a divisor. So the nodal locus has codimension 1 inside this moduli space. And then inside the closure of this locus of curves with nodes is the curves with cusps. And inside that is, so I guess essentially you can think of these as strata, where each one is contained in the closure of the space larger. So we have the nodal curves, and inside that divisor, there's the cuspidal curves, and inside that locus, there's this locus, but this is literally a curve. I mean, this moduli space has dimension 6. So this is a curve, so it has codimension 5, and then we have a single point. So in the GIT moduli space, they're not, this divisor, the complement of U is not normal crossing. It is indeed a divisor, but it's not a smooth divisor, or even like a log smooth normal crossing picture. As we talk about wall crossing, hopefully we'll see that this divisor starts to change. There'll be a family of moduli spaces, and it becomes smoother as you do these wall crossings. So this is only one choice of compactification. It's relatively nice in the sense that I could, as just writing down here, I can write down specifically the curves that appear. I can specifically write down the complement of U, as was just asked about. It's these curves drawn in the picture. And all of these curves are plane curves, but that's a choice that was made. There's alternate compactifications that we can study of the moduli space of smooth plane curves. So one that will be important in this talk, this is sort of an intermediate compactification. We'll call Hacking's compactification. And this is, the definition will be a little bit strange, but it uses ideas of polar Shepard-Barron. Shepard-Barron is one person, and the minimal model program. And the idea here is to remove ourselves, get rid of the notion that the limits of our plane curves have to be plane curves. Right? We might take a curve in P2 and degenerate it to some other curve that no longer admits an embedding in P2. How are we going to understand those? Well, we will regard our curve, instead of as in just a curve embedded in P2, as a pair. Right? So the benefit of doing this is that we could study degenerations of the pair. So now our surface that contains the curve might be a degeneration of P2, and our curve might degenerate to some singular curve on that surface. And what hacking did was include a coefficient in front of the curve. So let's say for alpha is 3 over d plus epsilon. Epsilon is some sufficiently small number. The pair P2 alpha C is minimally log general type, which for us is saying that KP2 plus alpha C is ample. This is the important consequence. But alpha is the sort of the smallest number that makes this happen. And hacking's idea was to use this minimal number to create, in some sense, a minimal moduli space of these log general type pairs, and used the minimal model program to do this. So I'll say this is due to hacking. We can compactify the moduli space. So I'll say there exists a space P bar H D to be pairs X alpha D, where a couple of hypotheses. X is a degeneration, a particular type, but a nice degeneration of P2. The divisor D is a rational multiple, Q linearly equivalent to the anti-canonical divisor of X. Oh, sorry, yeah, D over 3. This holds in P2, right? A curve on P2 of degree D. The anti-canonical divisor has degree -3, so this holds in P2. And this pair has at worst some conditions on the singularities. So, and I'll also say that D is ample. So SLC singularities are a particular type of nice singularities that you encounter in the minimal model program. They're the higher dimensional analog of what it means to be a nodal curve. Okay. And what's the theorem? I've defined this as a set, but in fact it is a DM stack, it's a DeVleming stack, and the theorem is that this stack is a compactification of our moduli space of plane curves, of smooth plane curves, so just the PD bar. So what's nice about this moduli space, maybe the observation to make here is that the curves, we have a condition on the singularities. So we have a condition that the pair has nice singularities. So the curves here are somehow less singular. The GIT moduli space had no condition on the singularities. Then those being parameterized by the GIT moduli space. Less singular overall, but they no longer admit an embedding into P2. So, to give an idea of what this looks like, again, let's draw another picture. So we have roughly the same moduli space. This is a compactification of the moduli space of plane curves. So in our first degree, again, D equals 4, we have two special loci again. So we have a codimension 1, so a divisor, that parameterizes curves on a surface called P114. So the pairs being parameterized by the pink curve, or the pink codimension 1 divisor, are curves on P114, which is a cone over the rational normal quartic curve, and C is a curve on that cone. If you are familiar with the moduli space of degree 4 plane curves, these curves are all the hyperelliptic limits of the degree 4 plane curves. But because they're hyperelliptic, this is maybe why one would expect that they don't admit embedding into P2. And it's easy to see these are hyperelliptic just by taking the structure of this cone, P114, and projecting away from the vertex. You get a 2-to-1 map from the curve onto a section. So a 2-to-1 map from the curve to P1. Inside this locus, we also have another special locus. It now has codimension 2, and it parameterizes curves on now something a little bit weirder, P112 union P112. I'm going to run out of space. And P112 is a cone now over a rational normal curve of degree 2. I'm going to glue 2 cones of those together, and then I'm going to take a curve on this cone. So again, if you're familiar with moduli of curves, to give you a little bit of a flavor, these are the curves that are elliptic bridges, if that means anything to you. And away from, again, the colored loci, the moduli space is in fact the same as the GIT moduli space. For H. So P for GIT. So the curves have, at worst, cusps. So just looking at this picture and noting that away from these loci, these moduli spaces are the same, we see that there's a birational map between these 2 moduli spaces, and we may hope to understand it in more detail. Okay. So I guess that's really the central question of the rest of my talk. I have these 2 moduli spaces. And they're birational. So it doesn't necessarily matter which way you put the arrow, but we'll say we have an arrow going from, the hacking moduli space, where we don't require that the curves admit embeddings into P2, to the GIT moduli space, where the curves are GIT semi-stable. How can we understand this map? Okay, can we interpret this map in a modular way? And what I mean by that, if you allow me 1 second to scroll up to the top of the screen, look at our older picture of the GIT moduli space. Try to always give some warning because I always get dizzy looking at a screen, scrolling very quickly. We have our GIT moduli space, and I have color-coded suggestively and these 2 moduli spaces have this rational map between them. But can we interpret that rational map? Can we resolve it in a modular way? Can I understand how to manipulate this moduli space and turn it into this, such that all steps of those process have a modular meaning? Meaning I can do all of those steps in families of the objects I'm trying to parameterize.
Is this the same as asking for like a natural transformation between the moduli functors?
That's a good question. On some level, yes, that's what we're trying to do, but there's not going to be a nice way to connect the 2 dots is the short answer. So maybe on some level, yes, but the answer to that is going to be no. There does not exist such a thing. But I think the answer, or even the study of this question, can prove to be a little bit surprising of how we approach it, because the GIT moduli space has one perspective of these curves in P2, stability with respect to some group action. If you're familiar with GIT, you look at these one parameter subgroups in the Hilbert scheme, whereas this moduli space just is like use the MMP to produce all the limits you want. So somehow they have these very different constructions, but those constructions are connected really neatly with this idea from differential geometry. And so what we can show is that the answer to this question is, can we interpret phi in a modular way? Is that yes, we can do so. We can interpret this in a modular way. And the intermediate steps, the way we translate from moduli space to another, will be creating a series of intermediate compactifications, come from a differential geometric notion of K-stability. So K-stability, initially it comes from differential geometry. And if you're familiar with GIT, I would say that it's algebraically similar to GIT. And by that I mean in GIT, if you're trying to determine if an object is GIT stable or GIT semi-stable, you take a one parameter subgroup, which is essentially a family of one object inside a Hilbert scheme. So you take a one parameter subgroup and you look at the sign of the Hilbert-Mumford weight of that subgroup. So this has something to do with how the action on this one parameter family relates to the natural action on the base of that family, which is A1. Hilbert-Mumford weight. With K-stability, we do roughly the same thing. Okay, well, if I could spell stability, that would be a good. Stability. We do roughly the same thing, but we take something more general than a one parameter subgroup called test configurations. So a test configuration is a one parameter family of a given variety or given object, but we don't require that the limit of that family, the degeneration of that family, admits an embedding into any particular projective space. It could embed into higher and higher dimensional projective spaces. But we take a test configuration and we look at the sign of something called a Futaki invariant, which is a generalization of the Hilbert-Mumford weight. So in a very precise way, you can think of K-stability as a generalization of GIT. Why would one think to look at K-stability for anything to do with this question? Recently, there's been a lot of work understanding K-stability and how it gives rise to moduli spaces of Fano varieties and log Fano pairs. So a Fano variety is a variety where minus kx is ample, and a log Fano pair is where minus kx plus d is ample. And this is a, maybe just to give an older theorem, which there's been dramatic progress on generalizing this theorem, but this is originally due to Li Wang and Xu and Odaka. This is there exist proper good moduli spaces parameterizing nicely smoothable. So the word Q-Gorenstein is the nice smoothings we are talking about. K polystable Fano varieties. And this has been really useful if you want to talk about fauna varieties. So, I mean, talking about moduli of projective space is maybe not so interesting, but if you want to talk about moduli of, say, cubic surfaces or something like that, you can build moduli spaces, compact moduli spaces of different fauna varieties inside the framework of K-stability. In our case, and maybe I'll just put many recent generalizations of this, because this theorem has really been generalized to remove the smoothable assumption, which was quite a lot of work due to many, many people. But we won't go into there. We'll talk about how this relates to us. But in the plane curve example, the curves we're talking about are not fauna, right? We have a curve inside P2, and the degree of C is at least 4. So in particular, C is not fauna. So we can't use K-stability to make moduli of the curves in this way, but if the coefficient of the curve is less than 3 over D, the pair P2 alpha C is a log phono pair. So we could use, just like we transitioned to talking about pairs in Hacking's moduli space, where we're talking about pairs where we are no longer requiring the curve to embed into P2, if I change my perspective and don't just think about a plane curve, but think about its embedding in P2, I can use the framework of K-stability to study log phono pairs. But in fact, I mean, in order for this to work, you need the following result of Odaka. This is his result is more general, but let's just say that if C is smooth, the pair P2 alpha C is K-stable. So the corollary of this is that my locus U, my locus PD of smooth plane curves. Oops. Oh, okay. Sorry. Something weird happened. Hold on. There we go. The locus of smooth plane curves should embed or be an open subset of the locus of K-stable log phono pairs or K-semi-stable log phono pairs. So I'll say it should live inside PKD. But I'm going to put a question mark here. Because what the theorem of Li, Wang, and Xu says is that we can make moduli spaces of phono varieties. But in fact, in this problem, we want a K-moduli space of log phono pairs. And this is maybe the first theorem of mine that I'll say in the talk, that not only do we have, Li, Wang, and Xu's theorem that say you can make K-moduli spaces for phono varieties, you can actually make K-moduli spaces for log phono pairs. So you can use K-moduli to not only compactify moduli spaces of phono varieties, but also of pairs. So this is with Kenny and Yu Chen, that there exist proper good moduli spaces. And if you're a stack person, you can say that there exist argent stacks and things like that. Parameterizing. Again, we have the Q-Gorenstein smoothable condition. K polystable log phono pairs. So there's a long sentence here. We'll say X alpha D, where a few hypotheses are satisfied. So X is phono. So like in the case of P2, this will work, or a degeneration of P2, this will work. And you want to fix some volume and dimension in order to get a well-behaved moduli space. The divisor D is a rational multiple of the anti-canonical divisor. so this is sort of exactly the setup that we have in Hacking's moduli space, except we're requiring that our pair in this case is log phono. So we're requiring that alpha is small. So, I mean, maybe the thing I should point out is that, right, alpha and R are fixed in this problem. So what we want to do is apply, I mean, I guess I should also say this holds more generally. So I know we're focusing on just plane curves, but you can talk about the entire framework of today's talk beyond just plane curves and talk about log phono pairs in general. So, right, what we're going to be, again, in today's example, we're thinking that, you know, X is P2 or some degeneration of P2, and, you know, D is, you know, either C, a curve of degree D, or a degeneration of such a C. So we know what R is, right? D is minus D over 3 times the anti-canonical. But how do these moduli spaces depend on alpha? So the theorem tells us for any alpha, right, we get a moduli space, say pk alpha d, but there are infinitely many alphas. So how useful is this? How do they depend on alpha? And this is perhaps the next theorem. And again, this holds in general, not just in the plane curve case, but as alpha varies, there are finitely many walls. So there are finitely many values where the moduli spaces change. That's what a wall means. And these wall crossings have a particular structure. So finitely many walls such that the K-stability condition does not change in the intermediate intervals. Let's try to write a precise sentence here for alpha in the interval alpha I plus 1. And the walls have a precise structure. So, you know, I don't have too much time left. I mean, I have plenty of time to say what I want, but I don't want to go over this in too much detail, but I'd like to tell you how these moduli spaces behave for plane curves. So what is these moduli spaces? What is appearing in these moduli spaces? And how does the boundary depend on alpha?
This finite collection of chambers,
Yeah.
is the number of chambers and I like the specifics of where the alphas are, is that dependent on X and D?
Yes, it's dependent on both. Yeah, so it depends on both X and D. It doesn't seem like there's I mean, even just in the case of plane curves, it doesn't seem like there's a well-behaved number of walls that one should expect. If you're familiar with, maybe I should write down a theorem that sort of gives some indication of this, and then I'll revisit what it means with your question here. So a theorem of Odaka says that if I have a log phono pair, then, and this is K semi-stable, then the pair is KLT, has some sort of mild singularities. So if you're not a singularity person, I mean, in particular, this says that the X is normal and has mild singularities. which are called log terminal. So because of this, this is one way you can see how these walls depend on the alpha. If you increase alpha beyond the log canonical threshold of the plane curve, or whatever the D is, it's no longer K-stable. That's not an if and only if. So K-stability, the case semi-stable or K-stability walls don't have to be at log canonical thresholds of a plane curve or any object, and things can destabilize before their log canonical threshold for other reasons. But at least this gives some indication of how this alpha comes into play and might change. So the singularities depend on both X and D. But I guess roughly what this is saying, as alpha increases, in order to have these mild singularities for larger values of alpha, your curve cannot be very singular. So if alpha is big, even if it was close to 1 or something like this, D has to be almost smooth in order for the pair to be KLT. So as alpha increases, somehow, as you're doing these wall crossings, D must get less singular, but X could get more singular. So as long as X doesn't cross the threshold of log terminal singularities, it can get more singular. So, I mean, the key to all of this is that in the case of plane curves, we can actually explicitly write down all of the possible X's. that appear. So there's a classification of all possible normal log terminal Q-Gorenstein degenerations of P2. So there's a classification of all the possible X's that appear in these K-moduli spaces. And perhaps, I mean, without telling you anywhere where this formula comes from, this is due to Manetti, this classification. And this says that this X, this KLT degeneration of P2, has to be either a weighted projective space, P A squared B squared C squared, where A squared plus B squared plus C squared equals 3ABC. So this somehow arises in many different studies of things that have to do with P2, but these are the possible log terminal degenerations, or it could be a partial smoothing of one of these spaces. So P A squared B squared, P A squared B squared C squared has 3 singularities. You could smooth any one of those individually. So if I want to construct the K-moduli spaces of plane curves, I have a list of all of the possible X's that appear. And I know something about how the divisor D should interact with the singularities of the surface X, because the divisor D, and we have some condition on the singularities here. So one could hope that you could just use this framework to completely understand all possible K-moduli spaces. And you can actually do that, at least in low degree. So this is hard in general, but we can definitely do this in low degree. And some statements about this in general. All right, but this has been maybe a nice little introduction to some facts about K-stability, but doesn't relate to our original problem. How does this relate to the original 2 moduli spaces we were trying to understand, the GIT moduli space and the hacking moduli space? Well, we can actually interpolate between the two using K-stability. So essentially the whole point is the K-moduli spaces allow us to interpolate between the hacking moduli space and the GIT moduli space in a precise way. So this is how we can connect the two moduli spaces from earlier in the talk. Okay. So we're not too much time left. So just to give a few of the highlights. Because of the similarity of the definition of K-stability and the definition of GIT, one might expect that there's some coincidental framework between them. And the first theorem is that for alpha sufficiently small, so maybe sufficiently small, sufficiently less than 1, the GIT moduli space is just the K moduli space. And same for the stacks. If you're a stack person, this isomorphism is on the level of stacks. This again holds more generally for hypersurfaces in Pn, but we'll leave it like this. And we can explicitly describe the first wall. Okay. So I'll just say, no explicit description. Of first wall crossing that comes from blowing up a particular point. And perhaps to illustrate this, we can just illustrate this with a picture of the same moduli spaces we've been talking about. So I'm going to scroll up quickly and grab my picture. This is one of the benefits of Zoom talks, I guess. You don't have to redraw pictures multiple times. And try to apply this framework just in the case of cortex and see what different moduli spaces you get. Oops. Okay. So in the case of cortex, how does this theorem apply? In the case of quartic plane curves, we have two moduli spaces so far, and we're going to understand this map by using intermediate K moduli spaces. So the theorem at the top of the page says that for alpha sufficiently small, the GIT moduli space is the K moduli space. And there's an explicit value of alpha. So this GIT moduli space is the K moduli space for any alpha, in this case, less than 3/8. And then you hit the first wall at 3/8 in K stability. And you have to do a blow up, a weighted blow up at this point QD. So we'll just say it's a weighted blow up. This is a Kirwan partial desingularization of the moduli space, if that's terminology that's in your wheelhouse. When you blow up a point, you get a divisor. So at 3/8, we cross a wall and we get a new moduli space, still for degree 4. We introduce a divisor, and you can construct these birational transformations, this blow up, in families. So you actually construct this, we actually construct this blow up on the level of the universal family of the moduli space. So we know exactly what's parameterized as we cross the wall. We know exactly that we get this divisor that parameterizes pairs on P114. Okay. And for any alpha between 3/8 and 3/4, this is the K moduli space we get. So in this moduli space, alpha is between 3/8 and 3/4. And all of the moduli spaces that you get are the same. And then at the very last wall crossing of the moduli space, last step of interpolation here, if you think about how the pairs in Hacking's moduli space were defined, right? These were pairs, P2 alpha D and alpha C and their degenerations, where alpha was 3/4 plus epsilon, 3/d plus epsilon. This is the alpha going from 3/8 to 3/4. So the very last wall in this case is actually at 3/4. And we get a moduli space, which will say P bar 3/4 Oops, I put my alpha as a superscript. P bar. 3/4 as an intermediate moduli space that you obtain on either side by contracting the blue locus. So this dotted line is a flip, and each side of these moduli spaces, we contract the blue locus. And so this moduli space at the bottom, again, has a very explicit description, and the image of the blue locus is well defined. So the blue locus gets contracted to a single point, and that single point parameterizes sort of the union, in some sense, of the singular surface here with the singular curve here. So the surface here was two cones glued together, and the curve here, that was the strict transform of this curve here, which had tack nodes. So this blue locus, the image of it, parameterizes a single surface where the curve has tack nodes. So I don't know how to draw this, but I'll just say curve with a tack node. And if you're looking at my picture and you're like, wait, you didn't tell me what happened when alpha was 3/8. When alpha is 3/8, this is actually isomorphic to the GIT moduli space on the boundary. So, I mean, roughly the idea here is that although K-stability comes from differential geometry, because the definition of K-stability looks very much like the definition of GIT, when alpha is small, it just recovers the GIT moduli space. And as alpha increases, we eventually get to this hacking moduli space where it crosses sort of a log Calabi-Yau threshold from the log Fano case to the log general type case. And the sequence of wall crossings we get in K-stability allow us to interpolate between one of these the GIT moduli space and this other moduli space. So I have maybe a minute left or something, and I'll just say all of these moduli spaces, the degree 4 case is really, really beautiful because all of these moduli spaces are also exactly what you encounter if you try to understand moduli of genus 3 curves and running the Hassett-Keel program or the log minimal model program on those curves. So this is the locus of pseudo-stable curves with cusps. So I guess you could do a blow up from here to get actual M3 bar. And then this is the first flip where you replace elliptic bridges with tack nodes. And this is the final step in the minimal model program, log minimal model program on M3 bar. So I guess I'll stop here with this picture, but everything that I've said, even though I focus specifically on the case of curves, generalizes to higher degree curves, higher dimensional objects, and different log Fano pairs. And so Kenny and Yuchen and I have been studying this in a lot of different ways to tell us a lot of information about moduli of other varieties. And in particular, we have work that's just about to appear on moduli of K3s using this framework, which I'm really excited about. So happy to answer any questions you may have, and thank you for listening. And thanks for the invitation.